Okay.
So I'm going to, if you came in a little bit later, I printed a page here. It's not a quiz or anything. We will, I mean, I don't want to write the whole problem on the board. And I probably will not do justice to the drawing, so I decided to just print it out. So let's go. We'll get to this. This is, it has to do with chapter 24. So we'll get to it. So, but for right now, we're going to do one final thing on chapter 23, which is the motion of dipoles on an electric field, or in an electric field. So remember what a dipole was? What was it?
Two positive and negative.
Yeah, a plus and a minus connected together, right? A plus and a minus connected together, and they're separated by a distance, let's say x or s. Okay. So, dipole. In an electric field. And then we get to the next chapter right after this one. So suppose you have an electric field that's pointing in this direction, right? An electric field that points in that direction, to the right. So here, it's everywhere. That's the electric field, right? So let me ask you, and suppose the electric field is uniform. By uniform means it has the same magnitude and direction throughout. Okay? How do you produce an electric field like this? Let's go to the right.
Positive on the left.
And then negative.
Positive on the left, negative on the right, or both. You can have both. So that will produce for you an electric field that way. Okay, good. So always keep that in mind. It means maybe there are positives present here and negatives here. That's how you produce such an electric field. So now let us put a dipole inside this electric field. Okay? So here is the dipole. The dipole will look maybe like this, a plus, and here is a minus. Minus, okay? So this one is positive Q, and this one is minus Q, right? So the positive Q will experience a force. In what direction will the force be on the positive Q?
Towards the right.
To the right. Because always keep in your mind, an electric field to the right means maybe there are pluses here, and pluses do not want the plus. They want to push it away. And or maybe there are minuses. The minuses would like the plus, so they would pull it. Either way, there is a force in this direction. A force in that direction. This is the force on the plus charge, and it is, or let me just this way. And that force is equal to, what's the magnitude of a force on a charge that's in an electric field?
K
Q1,
Q2 over R squared.
That's the force between two charges.
QE. Q times E.
Q times E. The charge times the electric field will be the force. Yeah, it's Q times E. Yeah. And yeah, I mean we use coulombs like K, Q1, Q2 over R squared to find the electric field, and then so eventually it goes back to that. This is a shorthand. Is that fine? Okay. How about this negative Q? In what direction will the force on it be?
Towards the left.
To the left. Yeah, pluses would like it, minuses do not want it, so it gets pushed down. Force, and it's of equal magnitude, right? It's Q times E. You might want to say it's minus, but I drew the arrow, so it's to the left, whatever it is. So what's the net force on this dipole?
Zero.
Net force is zero, yeah. There is a force to the right, a force to the left. So the net force on it is zero. Let me write it here. The net force is equal to zero. Does this mean nothing happens?
No,
No. What would happen?
it would straighten out to the horizontal.
It will straighten out. Yeah, it will rotate. It will rotate. Now, if it started horizontal already, it's not going to rotate, but right now it will rotate. So let's say this angle here is theta. Let's call it theta, right? And let's say the distance from here to here is S. So the distance from here to here is S over 2, right? Let me call it D for now. I think S looks too much like a 5. Can I call it a D?
Yeah.
Okay, right, D. Or if the whole thing is D,
D over.
so D over 2, thank you, D over 2. So the distance from plus to minus is a total of D, a distance D. The book calls it S, I'm calling it D. And so this is D over 2. So I heard there would be a rotation. Yes, there would be a net torque. So a net force of 0 does not mean a net torque of 0. And so if I pull on this page this way, sure, the net force is 0, nothing happens in this case. Because the net torque is 0, the net force is 0, nothing happens. But if I pull up and down, it's going to rotate until it gets straight this way. Okay. So there will be a torque. Now what is torque? Torque is the force times the distance from the force to the point of rotation times the sine of the angle between them. Okay. So force, or I'm sorry, the torque will equal to this. And I'm writing the magnitude of the torque, by the way. It's going to be a clockwise torque in this case, right? Don't worry about plus minus for now. So it would be the force, let's write it. It would be the force times the distance from the force to the point of rotation. So it's going to rotate about the center, right? And that distance is d over 2 times the sine of theta, isn't it? Okay. Similarly here, this one will experience the same amount of torque because it's going to rotate clockwise also. And it's the same distance, it's d over 2, and the same force. So plus f, and then d over 2, and then times the sine of theta. And this will add up to basically f times d times the sine of theta, right? The 1/2 and 1/2 add up to 1. That's the torque. And the force is QE. So you have Q times E times the sine of theta. Oh, did I forget D? I forget the D. Let me place it there. So you have Q times D times E times the sine of theta. And what did we call Q times D?
Oh, the momentum, dipole.
Yeah, that is the dipole moment, P. That's the dipole. Now, this is the magnitude of the torque. We should realize that if we would like to write it as a vector, so, before I write it as a vector, QD is P, so it will be P times E times the sine of theta. Now, when you see a sine of theta, if you see cosine, you should think dot product. If you see a sine, you should be thinking
Cross.
cross product. So it's actually the cross product of P crossed with E, the electric field. That's the one of those. And it makes sense, because the dipole in this case, in what direction is the dipole moment? Always points from where to where?
From positive to negative?
From
Negative.
from negative to positive. It points this way. That's the dipole moment. The electric field is this way, right? The electric field is to the right. If you do dipole moment cross the electric field, it will rotate clockwise, and you get a torque into the field. Okay? So it will be clockwise. Let's do an example. Okay? So suppose we do we get the exact numbers here. By the way, if you came late, I have a sheet here that you may want to grab, but do it a little bit. We don't need it right now until we start the next chapter. So here is the example. Suppose I have a dipole in an electric field. So I have my dipole, a minus, a plus, and let's say the distance between them, they're separated by a certain distance. And the distance between them is d equals to 2 centimeters. So 2 centimeters, okay? Suppose the charge on each of them, on either one, it's plus or minus, Q is, has a magnitude of 10 nanocoulombs. Nano means times 10 to the minus 9. So this one is negative 10 nanocoulombs, this one is plus 10 nanocoulombs. And let's say the mass of each of them has a mass of 1 gram. 1 gram. And they're in an electric field. So the electric field is in this direction. That's the electric field. And let's say the electric field is has magnitude of 10 to the 4th newtons per coulomb. That's the magnitude of the electric field. And suppose the angle is 30 degrees. Let's say the angle is 30 degrees. This angle is 30 degrees. The question is, find the angular acceleration. Angular acceleration means alpha. So how quickly is it going to rotate? So you put the dipole here and you let go. As soon as you let go, it will start to rotate. What's the initial angular acceleration? What's the initial angular acceleration? So let me write it down and then we go. So find the initial angular acceleration. Alpha is the angular acceleration. Remember this, in linear motion you have F equal to ma, linear acceleration is a. In angular motion you have tau, the torque, equal to, instead of mass you have moment of inertia, instead of linear acceleration you have angular acceleration. If you may recall this, tau equals to I times alpha. This is the torque, moment of inertia, angular acceleration. Okay, this is from 130. So now the torque, what is the torque? Well, it's a dipole in an electric field. So the torque will be, well, it's here. If I'm looking for the vector, it's P cross E. If I'm looking for just the magnitude, it's PE sine theta. I'm looking for the magnitude, so it will be PE sine theta. So I will have, for this, it will be P times E times the sine of theta. The right hand side will be the I times alpha. And now we will work on both. So alpha will be P times E times the sine of theta, which is 30 degrees, divided by I. So if I can somehow find all this information, I can plug it in. I know theta is 30 degrees, so that's already there. I know the electric field, it's 10 to the 4th. Moment of inertia is the charge times the distance between the charges times the magnitude of the charge. It's Q times D, right? It's Q times D. I know D and I know Q. So this one is information readily available. So let's write it down. So the P is Q times D. So let's write it. Q times D. Then E sine theta over I. So let's substitute some numbers. I will leave I for a moment. Q is 10 nanocoulombs, so 10 times 10 to the minus 9, because nano means, and then D is 2 centimeters, so that's 2 times 10 to the minus 2, right? They go to meters. The electric field is 10 to the 4th. Electric field is 10 to the 4th power, and then sine of 30 degrees. Over the moment of inertia. So I need to figure out the moment of inertia. That's what I need to figure out, right? So we have a dipole, it's rotating about the center. So what's the moment of inertia? You may recall for point masses, it's mr squared, right? M times r squared, the moment of inertia. So let's do some side work here. So if I have a mass m and another mass m here, and the point of rotation is here, this is r. This is r. This is r. So r is half of d, right? It's half of d, 1 centimeter. R is 1 centimeter. So the moment of inertia would be, yeah, let's do the word right here. I would be mr squared, m1 r1 squared plus m2 r2 squared. I have two masses. So the first mass is 10 to the minus 3 kilograms. And then the distance is, it's half of 2 centimeters, so that's 1 centimeter. So 10 to the minus 2. And then plus an additional one, which is the mass, 1 gram, that's 10 to the minus 3, times 1 centimeter, oh, it should be 1 centimeter squared, right? mr squared. Yeah. And then this one is 10 to the minus 2 to the power 2. So let's see what we get. 10 to the minus 2 squared becomes 10 to the minus 4. 10 to the minus 4 times 10 to the minus 3 is 10 to the minus 7. But I have two of them, so it would be 2 times 10 to the minus 7. 2 times 10 to the minus 7. What are the units for moments of inertia?
Kilogram meter?
Grams, meter squared.
Right. It's mr squared, so kilogram meters squared. Sorry, the table was on the way probably. Kilogram meters squared. So that goes here, 2 times 10 to the minus 7. Before you plug in numbers, just think about what you should get. You would have 10 to the minus 9 times 10 to the minus 2 is 10 to what power?
Minus
10 to the
11.
minus 11. This one is 10 to the minus 7 on the bottom. If you put it on top, it becomes 10 to the positive 7. But we have 10 to the positive 4. So that's 10 to the positive 11, 10 to the minus 11. When you multiply them, they just go away, right? So this power of 10, and this power of 10, and this power of 10, and this power of 10, they cancel each other and they just become 1. Well, I have 2 on top and 2 on the bottom. That cancels. And then I have 10 times the sine of 30, which is a half. Half of 10 is 5. So it ends up being 5 radians per second. That's the initial angular acceleration. Okay. I'm done with this one, with chapter 23. And let me pause the recording and start a new one so that the 2 chapters don't get, the new chapter and this one not